Just a century ago, the first commercial airline in history opened a liaison in Florida's Tampa Bay with a hydrofoil that could only take one passenger at a time. Today, 37 million annual flights transport 3.5 billion passengers either for business or tourism.
The growth of air transportation is simply a result of the development of the middle class.
In 2030, the middle class will represent the majority of the world's population, providing air transport to 6.5 billion passengers. The growth of air traffic is enhanced by emerging economies in South America, Africa, Asia, and in particular China, which will lead the world in this area.
It's a reality that between now and 2035 to 2040, there won't be enough landing strips for all existing planes.
To cover tomorrow's choice destinations, companies are forming alliances, creating new companies, while low-cost airlines are increasing their long-distance flight offers.
We obviously have to increase the space at airports in order to receive passengers in as comfortable a setting as possible.
With traffic doubling by 2030, air transportation faces many challenges. Concrete solutions are necessary in order to avoid saturation and flight delays.
We're going to be working on innovative functions on the ground as well as on board the aircraft to make this traffic fluid.
On the ground, the flow of passengers must be regulated to assure more takeoffs and landings, and in the air, the number of flights has to be increased while still assuring total safety. These are challenges for the aeronautics sector throughout the world.
One day, it'll all be automated.
We are going to discover the innovative functions being put in place on the ground and aboard the aircraft to keep traffic flowing smoothly. We're going to look at all the technological responses to the challenge of air traffic doubling by the year 2030 by following Max and Chloe, a couple travelling from Paris to Dubai. The driver drops them off at Terminal 2 of Charles de Gaulle Airport, one of the planet's 50 mega airports. Like all long-distance passengers, Max and Chloe arrive 3 hours before takeoff, the time needed for completing the different formalities. They dream of speed, not only on the aircraft, but during the checking-in procedures as well. At present, new technologies are appearing at airports to reduce long lines and waiting time on the ground. The problem is that these innovations have yet to replace obsolete systems still being used at most of the world's large airports.
The entire world of air traffic today can be broken down into about 50 big cities. We call them aviation megapoles. More than 90% of international long-distance flights pass by these 50 megapoles. We're talking about cities where all of its airports transport more than 10,000 passengers daily. With the growth of emerging economies, there will be more cities in China and other regions of Asia or Latin America. And we anticipate that in 20 years, there will be about 90 of these megapoles.
First stop for Max and Chloe, checking in. 66 million passengers come through Charles de Gaulle Airport annually. A third among them are simply in transit, but for the others, the road is long before they walk through the door of the aircraft. A host of passengers continue to check in their baggage and receive their boarding passes. And yet, it's now possible to avoid this obstacle.
Today, you can check in from your home or at one of the airport's check-in machines. We've also developed functions for automatically checking your baggage. The passenger creates his own baggage claim ticket and places his suitcase on a luggage belt.
Max and Chloe, adept at new technologies, have chosen the most efficient method. They purchased their tickets online, validated their boarding passes on their smartphones, printed their baggage claim tickets, and deposited their baggage at the express drop-off area. How can one make certain that baggage will arrive at the right destination year in and year out and not get lost along the way? By precaution, Max and Chloe double the company's claim ticket using this connected red label glued to each suitcase, a procedure invented by the French company Tracenet.
One misdirected valise per second, representing a total of 26 million bags throughout the world, and passengers numbering 3 billion, makes a lost bag a rare occurrence, except when it's yours. The main problem in such a situation is when the bag loses its passport, the famous airline paper claim ticket. If that happens, the bag is no longer identifiable. And so we've developed AeroTag, a mobile application that functions with an electronic claim ticket or a radio frequency system positioned directly on the bag.
One simply has to scan the boarding pass's barcode and the company's claim receipt, photograph the bag and enter some information. With air traffic in the process of doubling, tracing systems will soon be commonplace. Max and Chloe are now ready to check in their baggage. The drop-off system accelerates the operation to some extent, but is there an innovative solution for freeing their hands of their luggage as they go through the airport? Geneva Airport and CETA Lab have been experimenting with a robot baggage porter. Nicknamed Leo, the robot is stationed at the terminal entrance. The passenger drops off his suitcase, the robot scans the boarding pass and autonomously takes the bag to the sorting area.
Automation helps to improve fluidity, and that's an important development for the future.
The performance of baggage sorters is a major element for tomorrow's transport, first on a security basis with scanners capable of detecting the slightest explosive material, and secondly, for the speed and treatment of baggage until they're loaded onto the plane. Entirely automated systems will soon be deployed at all terminals. Max and Chloe are now heading for the airport's next problem, border control. As a result of increased security measures, they will be controlled several times before boarding the aircraft. At each point during peak hours, long lines form, one of the causes of flight delays. In the future, new identification procedures will increase security by rationalizing verification through random controls and selective searching of passengers based on their background or suspicious behavior. At the border post, travelers rush to present their IDs, making waiting and impatience the order of the day. Automated controls will be operational in the future with the goal of creating better security. People with biometric passports can use the Paraf lane. Paraf is a digitally controlled system which compares the print of a finger placed on a sensor with that of the passport. The Safran company is developing different identification systems as well as improving the digital capture mode of the Paraf system.
We've greatly increased the level of precision for reading a fingerprint. You no longer have to touch anything, which greatly speeds up things at the control area. This technology, which we call MorphoWave, allows us to read the print on the fly. A second technology which is coming into use is facial recognition. As soon as you're in the entry lock, you approach the cameras which take a few photographs. Then the treatment algorithm identifies your face and calculates it. We can recreate your face in 3D and check it with your passport photo. And so we verify that all the photos we took correspond with one another. There are certain characteristic facial points that never change, even if you've had plastic surgery, and they make for positive recognition. The third technology that we're using today is iris recognition. So today, our systems have attained a level of reliability so that we're able to capture the iris image on the fly. We can therefore acquire and match the iris in less than 1 second. We feel that in the long term, we'll have even more precise technology with much less chance of being mistaken.
The smartphone will be the key instrument of future travel, containing all necessary data from boarding card to hotel destination, as well as biometric captures. Passengers will be identified and then guided thanks to their smartphones. For facilitating airport procedures, for security purposes, and to accelerate operations, new strategies are being developed.
Throughout all of the airport formalities, camera systems, passage systems with fingerprint or iris recognition will make passenger traffic much more fluid.
What are the systems that will accelerate inspection of the passenger's hand luggage? Today, travellers have to remove all metallic and electronic objects and all liquid products, thus slowing down traffic considerably. The German firm Smith's Detection has developed a 3D scanner that can visualise a bag from every possible angle in a fraction of a second, an important asset for both security and inspection time.
The passenger arrives at the checkpoint, he can put his bag directly on the belt, don't need to divest the laptop, don't need to put the liquids out of the bag. It's a very smooth and direct process which scans the bag completely with X-rays, and we get a three-dimensional image of the bag, which has the advantage you can look from each side into the package. It's a transparent image, you see everything in quite great detail.
The body scanner can detect forbidden objects without resorting to a physical body search. The first models were scorned by the public because the images showed the real contours of the body. The new millimetric wave scanners not only show the passenger's body in the form of an avatar, but are much more effective in terms of detection.
The metal detector gates detect only metals. With the new security scanner, they detect all objects carrying on the body. So that makes the process much more convenient for a passenger. He doesn't have to get a full body search. He just gets, for example, at an arm and recheck. So that makes the process much more convenient.
The same German company has developed an application for following the passenger flow at filtering posts. This enables the increase or reduction of teams depending on the traffic. At Charles de Gaulle Airport, a control room exists to follow all airport activity post by post and hall by hall, thanks to numerous cameras set up throughout the terminals.
We estimate in advance how many passengers a day will be present at the inspection area to determine the number of teams we'll need, and then we act accordingly to the best of our ability in real time.
Is it possible to envisage an airport without lines or long distances to cover? Escalators and moving sidewalks are already reducing connection times by 70%, and thanks to the automatic shuttle, Max and Chloe gain additional time. On their way, they spot their plane taxiing to the area from where it will be loaded. Our friends arrive at the boarding area ahead of time, which is not the case for all passengers. 10% of them are responsible for flight delays. Either they continue strolling around the airport while boarding is being completed, or they forget a bag somewhere, which triggers the arrival of explosive experts. More than 2,000 interventions of this sort take place annually at Paris airports.
We're testing new technologies at the airport, like geolocalization, for example. You're scheduled to board a plane, but you're busy doing last-minute shopping at a duty-free shop. The aircraft is loading, and we know exactly where you are because you've established a connection with the airline via a social network, for whatever reason. And so we can send you a message reminding you that in 10 minutes, it will be too late to board. It gives passengers much more freedom, and it gives us better operational performance.
The search for better performance at all levels is a question of its economic impact. But will it be enough to respond to the incredible increase in air traffic?
There is no big country or capital city that doesn't have a large major airport. And if we want France to remain the world's premier tourist destination, we need to rely on our infrastructures like the airport, which is emblematic, and a gateway to the country.
Air transport is a key driver for European economy. Without that, the economy would stagnate. We saw what happened when we had the volcanic crisis. The European economy stopped.
The greatest constraints for European civil aviation are its airports. Some of them can add a runway or two, but the reality is that in 2035 or 2040, there won't be enough runways. We'll have reached absolute capacity.
We possess 3,300 hectares at Charles de Gaulle, so we've got room. We already have 4 runways, and so we can take on more traffic without having to build others. We're going to need more terminals, and we've got space for more passengers too, and several thousand square meters to build a new terminal in the future, capable of receiving 30 to 40 million passengers.
On n'est plus dans une situation historique où on faisait.
We are no longer creating terminals one after the other.
Ce qui compte énormément, c'est que les
What's important is that we are capable of receiving the greatest number of planes in close
Donc
contact.
ça veut dire que d'un point de vue forme en plan.
This means that today's airports are more compact, thus limiting gestures, movements and time.
En un seul moment, un peu sous la forme d'étoile de mer, si vous voulez, et qui fait que le centre.
They're built
est
like
à
a
égale
star with the
distance
center
de chaque
equidistant from each
avion.
aircraft.
Ça, c'est une
This is a very
caractéristique
important characteristic in the development of
du
airports,
développement
of
des
which
aéroports
China
et des
is the
aérogares
model.
en Chine. C'est ça le modèle. D'où cette
The
tendance
trend today is to
aujourd'hui de
design
voir
and construct
ces
them
terminaux
immediately
qui se
with their
dessinent
definitive
et qui
surface,
construisent
even if the traffic is
avec
not
leur
yet
surface
at capacity
définitive,
levels.
même si le trafic n'est pas encore là.
But how can the problem of runway shortages be solved? By creating endless runways, like this model by Henk Hesselink and his team of scientists at the Netherlands Aerospace Centre. On a minimal surface, this circular concept allows for the same number of aircraft movements per hour as a mega airport. Max and Chloe are reassured. They can see their plane. But will it take off on schedule? Some companies estimate too short a loading time, thus creating delays. Eric Prévost is the pilot aboard Max and Chloe's plane. The latest weather data has just arrived, and he studies the Paris-Dubai route with his co-pilot. All the flight plans of the 2,000 companies operating in Europe are sent to Eurocontrol, the European regulating organisation. This represents 30 to 35,000 flights per day.
We're now in a European centre helping air traffic control centres to manage airspace for 41 European countries.
In 2015, a uniquely European project created the CESAR programme, which regrouped a number of technological solutions. Major players in the aeronautics sector united to harmonise air traffic and make it safer.
We're developing new technologies, going from a simple flight plan, which describes the routes and so on, to a much more precise description of trajectories to the nearest few seconds. When you have that sort of precision, air traffic control can manage more aircraft and gain 5, 10 or 15% capacity. There's a lot of work being done by all our civil aviation partners, although the percentages of gain remain small.
Max and Chloe observe the activity around their aircraft. Captain Prévost is checking the last controls affected, while his co-pilot, before going on board, inspects the plane, a required step before takeoff. In the meantime, the Boeing completes its refuelling. Air transport consumes 5% of the world's oil consumption every day. A European programme is aimed at reducing this environmental impact by cutting kerosene consumption in half.
We're at a crossroads. There are new tools appearing in cockpits. We're developing exchanges between the aircraft and the ground. Constructors are developing a number of automatic tools which can facilitate the work of the pilots. It's not a question of man and automation being in competition, but on the contrary, to possess a system with greater competence and effectiveness.
To design its prototype of a future cockpit, the Thales company, the world leader in electronic aeronautics, has appealed to numerous professionals: pilots, engineers, psychologists, doctors, and experts in man-machine interfaces. The goal is to increase the amount of information available to the pilots.
It's the cockpit that enables the plane to be at the center of the aeronautic ecosystem by connecting it first to the ground, that is the airline, and secondly by digitally connecting it to traffic control, thus returning data back to the plane which the pilot doesn't have or has very little of today, and especially data in real time.
Thanks to the cockpit's entirely tactile surface, the pilot can reorganize the screens to his liking.
Here we have a three-dimensional view of the airport, and here a 2D view with which we can control airport navigation. The route at this time is blue, and it can follow the path as we might on a car's GPS. We also see the movement of the airport in 3D, so the pilot can taxi without error.
With this new generation cockpit, the pilot receives weather, route, and trajectory data electronically and not via radio contact.
The advantage of a written message is that it considerably reduces the risk of error in the transcription of someone giving the order orally, through a radio system whose quality can differ between one area and another. It also avoids language barrier and accent problems, for example, thus assuring that the information is correctly received by the pilot. This connectivity via the cockpit gives him the data he needs to make the best possible decision. One of the goals of these new technologies is also to create the greatest possible air traffic fluidity.
What, however, can be done in the event of a computer breakdown? With all these interconnected systems, isn't there a danger of piracy or a cyber attack?
The architecture of the systems being designed for the aircraft, the infrastructures and the ground systems all take into account the risk linked to cybersecurity. All of these constraints are integrated into the conception and the architecture of the systems. This is another reason for always having a pilot in the aircraft and controllers at control centers, so that in the event of a malfunction, the system scan can be taken over by the people involved.
Okay, we're taking up too soon right now. Clear left. Clear droite. Before taxi checklist complete.
Pilots go through a checklist to guarantee that all the instruments and equipment respond faultlessly. Three hours after their arrival at the airport, Max and Chloe finally board the plane after a final formality, this time by the airline. A few more steps and they take their seats on the Boeing 777. This is not the case for some passengers who remain on the ground as a result of overbooking. Companies actually sell more tickets than there are seats on the aircraft, since they anticipate that, for various reasons, some people will not take the flight for which they reserved. In addition, any incident occurring on a previous flight could lead the airline to give passengers priority on the following flight.
Air France 662, good morning. Okay for start-up and pushback.
Oui, j'écoute.
Je peux libérer le frein de parc?
Oui, sans problème.
Tractors help planes leave their parking zone. Gradually, their motorization will go from diesel to a more ecological electric version. Soon, tractor robots will accompany the plane to the runway. Another, more economical and quieter technology for taxiing will incorporate an electrical system in the wheels of the aircraft, which will also be used for landing. Permission to taxi is given by the tower controllers, and so our pilots are waiting for the OK.
In the past, a plane which was ready could taxi and be led to the stopping point, and then there'd be a series of annoying takeoff sequences which encumbered the ground space, making things very complicated and ineffective. Because when you got to the runway, you were number 16 on the takeoff line. You had to wait with your engines running and consuming fuel. Just because a plane is ready to take off doesn't mean it will take off. It's a complex situation, since you've got arriving and departing aircraft crossing each other, and so you have to create a departure sequence, and so you're led to a stopping point on the runway. The ideal is having between 5 and 10 planes waiting to take off, but no more than that.
Air France 662, hold at Tango Kilo 3. Another aircraft is taxiing into Kilo 71.
As soon as he receives the order, Captain Prévost taxis to the takeoff runway. With all the technical vehicles moving in all directions, circulation is under strict surveillance. 1,400 planes land and take off from de Gaulle Airport every day. Controllers assist pilots, and computerized onboard maps enable them to find their way through this maze of lanes and roads. And yet, pilots can still lose their way and cause a host of delays. To improve traffic, especially when there is fog, the Experimental Centre of Eurocontrol is testing new software.
We have a system where a series of green lights is all he has to follow, and that will direct him to where he needs to be when he comes into park, when he lands, or when he's taxiing out to go to the runway.
Thanks to radar, the position, altitude and speed of each aircraft appear on the controller's screens. These data are communicated to the pilots by radio. Although they know the characteristics of the flights, they intervene only at the moment they enter into their sector.
We actually don't know if a plane is late or early. We manage the flow and constantly accelerate traffic. We guide the planes to optimize things for everybody. Of course, we have the radio. We're in constant communication with the pilots. If we lose a screen, we have backup screens. Although if there's no radio, we can't communicate, meaning we can't manage the traffic.
Better air traffic management is indispensable to handle the increase in the number of flights. Tower equipment and control centres have to be modernised, and a new work methodology has to be created.
It's a constantly evolving profession, and so we have weekly briefings dealing with new tools, new procedures, and new aircraft. We have to take into account everything that's new.
Our plane patiently awaits permission to take off.
Today, we tend to work flight by flight, trying to optimize a number of flights and the steady flow of flights. A lot more things have to be calculated, which will automatically be generated by the system, permanently leaving the mastery of the control to the controllers, who will have access to more information.
The Thales Group is at the forefront of important innovations for optimizing air traffic through electronic systems and aircraft equipment, as well as for control centers.
Air traffic controllers see each flight as a paper strip that has flight information associated with it. In the future, they will use what we call electronic flight strips, which will present the information digitally to them and allow them to very dynamically see changes. If an airline delays a flight, the new availability for pushback of that flight will show up in the electronic flight strip and on the display, and allow the controller to very dynamically know that there's a change in the plan and to adapt the operation on the airport surface to match the new demand.
Radar, radio, and landing help systems at airports are extremely reliable. Delays are almost always due to our inability to control the weather. If, for example, there's fog in Madrid, the flight will arrive late here. If we have nimbus clouds over Paris, it will create delays through other parts of Europe. Airport capacity depends on the runway.
Bad weather can cause numerous delays if it's not anticipated. At Charles de Gaulle Airport, if there's fog, the number descends to 44 per hour. We're in the Île-de-France region, economically the first in France. And so the slightest problem can create important financial problems. Certain aircraft can land with 0% visibility, but others can't and need at least 400 meters of visibility. It's the same for the wind. Some planes can't land when the crosswind attains 38 knots. So we have to anticipate these winds and organize a precise chronology to ensure totally safe landings. And since we can anticipate strong winds 9 hours in advance, we try to land aircraft either a bit early or a bit late.
Digital models can fine-tune predictions as well as spot them. Thanks to a grid, potentially dangerous atmospheric conditions can be localized by specific sectors.
The problem is that these models generate an enormous number of calculations, so we need powerful machines. At present, at the French National Weather Bureau, the supercalculator can execute 14 billion calculations per second. If we want to lower the mesh by half for a fine mesh model, we have to double the number of calculations per second. Since computers that can also perform so many calculations don't exist as yet, we're technologically limited.
Air France 662, good morning. Line up on runway 26 right and wait for clearance.
Our airplane's departure is imminent, ready for takeoff. Their safety belts fastened, Max and Chloe are ready to go. But our captain has to await authorization from the controller to take off.
Air France 662, 200 degrees, 3 knots, runway 26 right, cleared for takeoff.
Cleared for takeoff, runway 26 right, flight 662 Air France.
The aircraft leaves the ground at 250 kilometers an hour. The Thales company has developed a new procedure included in its cockpit design. By automatically adapting the speed, the altitude, and the engine thrust, it reduces the fuel consumption, CO2 emissions, and the noise heard by residents living near the airport.
The present limitation to air traffic on landing is the time the runway is occupied, and on takeoff, it's the wake turbulence.
Wake turbulence is created by the movement of the aircraft in the air and by its weight. A small plane in the wake of a large passenger plane can literally be turned over by its violence, which explains the distance separating two planes at takeoff and landing. To make air traffic more fluid, we therefore have to reduce these spaces. To accomplish this, scientists at ANERA are working on LIDAR, a laser detection instrument that can establish very precise maps of air masses.
The LIDAR will allow air controllers to visualize these whirlwinds and know how long they will last above the runway. In the context of aerial safety, it can be very useful, especially for measuring the space needed between planes. When there is strong atmospheric turbulence, in 30 seconds, the wake is completely dissipated. The gain can be fairly important if there's strong wind or turbulence, which can destroy the wake swirl.
The LIDAR will be placed on the side of the runway for measurement purposes. It will also be installed on board in order to identify turbulence up to 10 kilometers in front of the aircraft. Turbulence disturbs passenger comfort, and if the pilot is aware of what's coming, he can navigate around it.
Flight 662, good morning. Climb to level 260. Velocity is free and proceed to Louval.
Level 260, velocity free and direct Louval, Air France 662.
A plane goes from one space to another. The flight path and shortcuts don't really matter, since it will be constantly in contact with the controllers whose job is to assure the security and optimization of the trajectory and velocity in order to guide the aircraft to its destination at the airport and its parking zone.
Air control centres are implanted in every country. There are 5 in France. Planes use specific air corridors, and the controllers watch over their vertical and horizontal separation to protect them from any risk of collision.
The first step today for Europe is to raise all of these control centres to the same level of technology, so as to be able to introduce new functionalities.
We have 65 air traffic control centres in Europe with different systems. So one of the efficiencies that we are making is that these systems have to speak to each other and be seamless, so that they can link to each other. The airlines fly all over Europe, all over the world, so they need the global technology, the global systems, the global navigation systems in order to travel.
The European SESAR project is close to the American system in order to assure that these technologies can, in spite of their differences, connect to each other without interference.
In fact, if you take it at a global level, there is ICAO, the International Civil Aviation Organization, which have their global air navigation plans.
Flight Air France 662, due to military activity, the route will be Louval and then Épinal.
Louval then Épinal, Air France 662, thank you.
A flight is never totally straight from one point to another. There are forbidden flyover zones. This is the case for the Paris-Dubai route.
There are zones that you see here that are colored, meaning there are restrictions for civil aircraft because of military activity. So a plane which wants to take a route that goes through these zones will now have to take another further south, which will add several minutes to the flight times.
Within the context of a unique European sky, ideas are forming for restructuring airspace. The very existence of routes and air corridors are being called into question. Tomorrow, pilots should be able to follow the trajectory they want. It's called the free route concept. Simulations are now being made by Eurocontrol engineers.
What free route will do is remove the route network in its entirety, is the eventual concept, and we will just have entry and exit points into a volume of airspace. Between the entry and the exit point, the airline or the operator is able to fly exactly as he wishes. Now that can be a direct short path, which means increased fuel saving because they're flying the shortest route available, or if there's a day where there are particular winds, they could fly a curved route which will take them away from the wind and will give them the most efficient route for them on that given day. Every single development brings a small increase. There's nothing that is going to completely transform aviation immediately.
Today there are 3 dimensions to trajectory management: altitude, longitude and latitude. The SESAR program implies a flight development in 4 dimensions, adding time to the other 3.
One way of making air traffic more fluid is for planes to be capable of mastering their precise passage points and managing time with precision. This is a major factor for increasing air traffic, since it gives us a better idea of landing times, thus improving the flow of traffic. Our system has demonstrated that it is possible to be precise to the nearest 10 seconds or less on a point defined in advance by air control, thanks to the performance of the systems on board the aircraft, as well as the tools we deploy on the ground for air controllers.
Night has fallen over Flight Air France 662. The aircraft's cruising speed as it heads for Dubai is 950 kilometers an hour. Part of the future equipment includes a satellite liaison. This system of navigation is indispensable for crossing zones where air control cannot operate.
When you cross the Atlantic, you have no radar coverage. Planes today are spaced 10 minutes apart, 10 minutes or about 80 nautical miles or approximately 150 kilometers. This means that every 150 kilometers you've got one plane behind another, which is not optimal as regards space occupation. With this new connectivity technology, we'll be able to send information via satellite to air control, which will describe the situation as if there were radar cover. This is a huge development, and there will be planes equipped with these new technologies which will be able to integrate themselves naturally into the flow of traffic with optimum trajectories in the space and in the time between the controllers and the pilots and others who don't possess this level of equipment, and therefore will not have access to airports and air corridors that will enable them to make better connections.
Pilots exchange data with both air control and their airline. The control centre of the Air France's aerial operations, the CCO, follows its aircraft through the world's functioning 24/7.
The CCO's mission is to assure smooth running of flight programs in spite of unexpected events of all kinds, including weather problems, breakdowns, unavailability of a flight team member, geopolitical crisis in Africa, a problem of airspace saturation, the closing of an airport, or restrictions. All of these phenomena will be taken into account and the best decisions will be reached without delay.
A medical problem on board requires attention.
I'm calling for Air France 253 flying back from Saigon and scheduled to land at Roissy at 1600 hours. I don't know, I've got them on the line. They seem pressed for time and want to land in less than an hour. There were doctors who wanted to talk to their paramedics right away. Air France 253, you can talk to the paramedics.
He's been in pain for about 2 hours. We had him lie down, but the pain is getting worse. It would be best to land at Charles de Gaulle as scheduled, since it's the closest, because by the time you found another airport, you'd already have landed. All Air France planes are equipped with a system for sending us their position every 4 minutes. And this position is transferred to the follow-up screens. Punctuality is a key element. A flight that leaves late can create delays of several other planes in a sort of chain reaction.
Our flight continues without a snag. Delays are often due to breakdowns or malfunctions, the scourge of airline companies, especially when an aircraft is immobilized at a distant site where spare parts and mechanics teams are not available. Thanks to big data, maintenance has become predictable, and it's possible to detect malfunctions before they happen.
For the past few years, Airbus has been developing software using sensors on board the aircraft. Of the 350, we have 400,000 parameters available per flight that reflect the behavior of our systems. We can recover this on-board data as soon as the plane lands or even prior to landing. What we need now is to equip planes with more powerful recording instruments along with more powerful communication equipment on the ground.
Tomorrow's aircraft are those which are being ordered, manufactured and sold today. By 2030, the major part of the larger airlines' fleets will have been replaced by a new generation of planes.
It's important to note that between the time you order a plane and the moment it flies for our company for the first time, years can go by. And so there's a lot of work involved to determine if the plane we're ordering at great expense, a long-range aircraft, for example, costs $200 million, is a valid purchase for the future. 2030 for us is today. If, for example, it's a Boeing 767, we know we've got a technological jewel, both in terms of durable development and the ecological effect it has on the planet. It's much less noisy both outside and inside the aircraft. We don't take air from the engines. We manufacture the air which is aboard the plane using electrical systems. We have much better control of the humidity level aboard. After a 12-hour flight, you feel much less fatigue.
Airlines will be requiring larger and larger planes since, by adding more passengers per flight, their costs are greatly reduced. It also compensates for problems of congestion. With air traffic increasing by 4.5% annually, it's bound to double every 15 years. And so it's much simpler to have bigger planes for more passengers than to proliferate the frequency with smaller models.
A large plane like the Airbus 380, however, will not represent the wave of the future, since necessary infrastructures cannot be handled by all airports. The length of service of a passenger plane is about 30 years. 400 passenger aircrafts like the latest Airbus 350 corresponds better to future needs.
The structure is made out of carbon fiber. Carbon fiber is a very light material, very strong, very stiff material, and therefore it allows us to reduce the weight of the aircraft. Second, we have a wing. I call this an intelligent wing, because this wing, first of all, has the fantastic aerodynamic design, and this wing, once the aircraft is airborne, can adapt to the flight condition. When you see here the trailing edge, the flaps, depending on the loading, depending on the speed and the height of the aircraft where it's flying, it adapts the profile so that it always worked in a very efficient way.
The aircraft of the future will be lighter in order to consume less fuel. It will take off faster, thus enabling it to increase its rotation frequency. Companies can also increase the plane's weight capacity to accommodate more passengers on board. Ingenious minds are inventing the plane of the future, like that of designer Oscar Vinayas, which is fueled by hydrogen with cabin energy supplied by solar panels, making its ecological impact almost non-existent since the aircraft only emits water vapour. The Technicon design agency is developing an aircraft, the Ixion, without windows in order to reduce weight and offer passengers a unique travel experience. The windows are replaced by screens which project panoramic images. They are also connected, giving passengers the possibility of seeing films or participating in video conferences. Beyond cabin equipment and motorization, daring new ideas are guiding the future of air transport, like the modular aircraft developed by the Lausanne Polytechnic School.
We're going to use the same engines and the same material used by planes being developed today and in the future. What we're concentrating on is the way in which a plane is handled and utilized. We're creating a system of modular aviation, meaning we can change modules, which we call capsules, and these capsules can be either passenger or freight capsules. The wing, which can transport 3 of these capsules, will allow for the transport of about 450 passengers. In short, these capsules will be slid in under the wing and then clipped on underneath. This operation should take 15 to 20 minutes. There's no need to be concerned about specific airport zones, since this type of plane can land and take off normally like any other aircraft.
Companies will thus be able to manage the capsule capacity more effectively by varying their passenger and freight requirements.
This plane will have parts that can leave the airport area, meaning that the sorting will have already been carried out. So passengers will already be loaded in the capsules. In short, we try to copy what containers do with profiled containers for travel at 900 kilometers an hour, or for travel by train, or even by road.
This concept of capsules is still in its infancy stage, but it has already attracted many players in the aviation industry. Max and Chloe's flight is coming to a close. Their plane has begun its descent on time to Dubai under a clear sky. It sometimes happens that when traffic is heavy, many airports keep aircraft on waiting circuits called hippodromes.
There's no sense in arriving ahead of schedule if you have to wait for 20 minutes above a beacon marker before it's your turn to begin your approach and land. So today, with the I4D plan, we can have an exchange between the cockpit of the controllers and anticipate in real time the speed necessary for arriving at the right place at the right time and minimize delays on arrival.
Continuous non-stop descents will soon be generalized. This will reduce fuel consumption and noise problems because there will be less acceleration. Another procedure now being tested deals with planes no longer being guided by controllers, but by following a programmed trajectory for reaching the angle of the runway.
We prescribe a leg which has a curve on it, and the controller can then judge at what point to turn the aircraft in, and it means from the aircraft point of view, they are much higher than they would be today when we use radar vectors, because today we radar vector, we descend, we extend them on a downwind leg and then turn them in. With point merge, they tend to arrive at a higher level, and once they're given clearance, they take their own descent, so it's much more efficient in terms of fuel burn and environment, and then they come in and they're sequenced into final approach.
One way of managing the increase in air traffic is for planes to be able to land under any weather conditions. Today, when visibility is very limited, aircraft depend on ground guiding systems to land, but not all of the world's airports possess them. To maintain the rhythm of landings in the future, planes will have to overcome ground constraints with new tools such as the Top Max headset, known as Eyes Out.
Ces technologies de visualisation tête haute peuvent être couplées à des
These
caméras thermiques
eyes-out
qui permettent
visualization technologies can be combined with thermal cameras that can see through cloud layers,
opérationnelles supérieures à l'avion, et donc ainsi augmenter
thus
la
giving the
fréquence
aircraft superior
d'atterrissage des
operational
avions sur
capacity.
les aéroports, quelles que soient les conditions météo.
In this way, the frequency of landings can be increased, regardless of weather
de
conditions.
fluidifier le trafic.
New technologies are ready for the challenge of the air traffic doubling between 2030 and 2040. In 20 years, Max and Chloe's journey will have undergone many changes. For the aircraft, there will be optimized trajectories, a permanent connection with towers and control centers, and information in real time. On the ground, there will be permanent and powerful systems to assure more takeoffs and landings. For passengers, check-in methods and automatic controls will speed up the formalities, and digital informations will guide them more effectively. These modernization procedures, however, will take place gradually, the result being that in the next 2 decades, old and new systems will cohabit with each other. Some airports will have to adapt to the increase in the number of flights and avoid the accumulation of delays. Only after the next revolution in air travel will aviation move totally from one era to another. After a 6.5-hour flight spanning 5,240 kilometers, Max and Chloe disembark, impatient to discover Dubai. Barely 2 hours later, their aircraft will leave for Paris with a new flight crew.